Alright guys, so I just want to make a quick video to introduce you to distributions. Alright, so we are going to go straight into it. You may remember these two terms, discrete and continuous. We talked about those back in, like chapter 3. Remember, we talked about discrete data. Discrete data was data that you could count, right? 1, 2, 3, 4, or even 1, 1.5, 2, 2.5, like shoe sizes or something, right? That's discrete, where you can count it because it does have very specific or discrete values that can occur. Okay. The other term that we used at that time was continuous, and continuous is something that we measured. You measure a height. There's always something in between, any two numbers. You can choose any two numbers, and you can always find something that's in between those two because it's completely continuous, right? And so discrete and continuous, we're going to be focusing for today on discrete. Okay, and we're going to be looking at discrete probabilities. We're going to make some connections between what we learned before and what we're learning now. All right, so discrete is the first thing we're going to be looking at discrete probability distributions. Eventually, we'll get to continuous as well, but today, discrete only. All right, so the first thing I want us to do is let's consider a die. All right, so this is going to be a slightly different kind of die. All right, it is a normal six-sided die, but instead of having the numbers 1, 2, 3, 4, 5, 6 on the sides, it's going to have 1, 1, 2 2s, and then the other three sides are going to be 3s. All right, so 1, 1, 2 2s, and 3 3s. Now, I would like us to build what's called a probability distribution table. And this probability distribution table is going to show us the probabilities of each of these numbers. Now, these numbers are what's called the random variable. So we can say, for example, here that x is the random variable. In this case, a discrete random variable. All right, and so what we're going to do is we're going to create a table here. And we're going to say that x, the random variable, can have certain values, right? Now, with my special die here, there's only 3 values that it can have. It can have a 1, it can have a 2, or it can have a 3, right? Now, in the second row, we're going to put the probability that x equals a specific number, all right? So in this case, right here in the first square, I'm going to put what is the probability that I'm going to get 1. All right? So if the probability of getting 1, there's only 1 out of 6 sides. So that would be 1 out of 6. All right? We move on to number 2. There were 2 2s. So the probability of that would be 2 out of 6. All right? Now there were 3 3s. So the probability of getting 3 is 3 out of 6. Now, this is a discrete probability distribution, all right? Now, one thing that should be noted here, a couple of things, right? We always have the values on the top, and then we have the probabilities on the bottom. Now, if this is a proper probability distribution, the bottom should all add up to equal 1, right? 1 6 plus 2 6 is 3 6 plus another 3 6 is 1. So we add all those together, we get 1 or 100% because that's how probability should work. There shouldn't be any unknown thing there or any number that we just don't know what it's going to be. There are specific values that have to come out, right? And so these are the only 3 values that we can get rolling this special 6-sided die. All right, so let's go ahead and look at a couple of other examples of probability distribution functions, and we'll just work through a couple of problems associated with this. All right, so one other term that we need to look at is a probability distribution function, which often is just called a PDF. Now, a probability distribution function is a function that represents a probability distribution. Or in other words, it's a function for which the sum of all the probabilities is equal to 1. Okay, if all the probabilities add up to give me 1, then it is a probability distribution, and this function that represents that is a probability distribution function. All right, so look at this one right here. I've got f of t equals t minus 2 over 15, where t is integers from 3 to 7. All right, we want to show that this is a discrete probability function, a discrete probability distribution function. All right, so we're going to make our table of values just like we did before. Okay, we will put our values up in the top. What are the values that, sorry, we're not doing x here, are we? We're doing t. So what are the values that t can be? Well, it can be every integer from 3, 4, 5, 6, and 7, right? Now, what is the probability that x is going to be equal to that specific value? Well, if I put 3 in for t, right, then I have 3 minus 2 over 15. So that would be 1 over 15. Then I'm going to put the 4 in. I'm going to have 4 minus 2 over 15, which is 2 over 15. And if I go ahead and put all those in, you can double check me on this if you want. I'll have 3 over 15, 4 over 15, and 5 over 15, right? Now, to show that this defines a discrete probability distribution or a probability distribution function, what we're going to do is we're going to add all these together. 1 over 15, 2 over 15, 3, 4, and 5, which if I do add those together, I get 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15 over 15, which is 1. Therefore, this function, f of t, equals t minus 2 over 15 from 3 to 7, as long as t is an integer, then this right here is a probability distribution function. All right, so let's look at another example. All right, here we go. We've got a fair cubical die and a fair tetrahedral die, which are both thrown. The discrete random variable s is defined as the sum of the numbers on the two dice. So we want to construct the probability distribution of s, and it wants us to do a table of values. So we are eventually going to do that, right? So we're going to put s here, but we may not know right off the top of our head. Let's see, that's the probability that x is equal to that s value, okay? We may not know off the top of our head what those probabilities are. And so now we're going to have to use some of the things that we learned in our previous units. This is 2 dice, which seems to me a fairly good reason to do the sample space diagram. So 1, 2, 3, 4 on the side. That would be a fair tetrahedral die that has, tetrahedral has 4 sides. That's the tetra, actually. That's why Tetris is called Tetris, because all the blocks have 4 blocks in them. So 1, 2, 3, 4. All right. And then on the top is a cubical die. So that would be 1, 2, 3, 4, 5, and 6. So now in each of these, in my sample space diagram, I'm going to show what the values of s can be. S is defined as the sum of the numbers of the 2 dice. So if I roll 1 and 1, I get 2, 3, 4. Go ahead and fill this out. I'll give you a second. I'm going to do it as well. And hopefully this is what you got over here. So now what you can see is I have some values everywhere from 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 10. So my table here says that s could be 2, 3, 4, 5, 6, 7, 8. I'm going to run out of space. This is a big table, y'all. It's all right. Big tables. Big tables mean lots of food, right? Oh, wait, not that kind of table. Sorry. All right, so 2 up to 10. Now, what's the probability of each of these, right? There are 24 total boxes. 1 out of those 24 is 2. 2 of those 24 is 3. And go ahead and finish this table. All right, so hopefully this is what you got. Go ahead, take time to do it. Pause me if you need to. I paused you while I did it. So go ahead, fill it in. Recognize I left all my denominators as 24. You don't have to do that. You can reduce these if you want, especially if you're going to do some mathematics with it later. And then initially I left them all as 24 because that's going to make it really easy for me to add them together. 1 plus 2, because the denominators are all the same. That means I can do 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 14, 18, 21, 22, 23, 24. So I made sure that when I add all of them together, I get 24 out of 24, which is what the probability distribution should be. It should add up. Those are the only possible values. There's nothing else possible for these two dice to add up to. All right, so we have our probability distribution table. Now, this asks us to do a couple of things with it. It asks us to do a bar chart. That you can do. Okay, so you just make a little bar chart down here. You put your values at the bottom. 2, 3, 4, 5, 6, 7, 8, 9, and 10. Lovely. And then you can put your bars on there. Okay, so here you can actually put whatever you want on the side. If you want to turn it into a decimal, you can. I'm going to just leave it as 1 over 24, 2 over 24, 3 over 24, and 4 over 24. And then when I do that, the 2 should go up to 1. The 3 will go up to 2. The 4 will go up to 3. I'm just reading these off the top chart there. And then 5, 6, and 7 are all going up to 4 out of 24. 8 goes down to 3. 9 goes up to 2. And then 10 only goes up to 1 out of 24. And so there's a bar chart. Nice and visible, helps you see what the distribution looks like. Okay. The next one's a little bit more challenging. It wants us to do a piecewise function. So it actually wants us to write the function for these. Okay. Now what I see is that I'm going to have some slightly different functions, right? I see it going from 1 to 2 to 3 here. Okay. Between 2 and 4. So if S is between 2 and 4, I think I'm going to have one function. And then from 5 until 7, it's always 4. So from 5 until 7, I'm going to have another function. And then from 3 to 1, 8 to 10, sorry, I'm going to have some type of different function. All right. Now, in order to be able to do this, I'm going to try to come up with some type of function for this, right? Now, the first function should be pretty easy, right? Because it goes 1, 2, 3. So each one of these we'll notice is 1 less than S. So if I just go S minus 1 and then put that over 24, so this is f of x, and then we're going to do our little thing here and say this is equal to, so from 2 to 4, it's going to be S minus 1 over 24, right? Because it's always S minus 1, S minus 1, S minus 1. Okay, now from 5 to 7, that one's pretty easy as well because it's just 4, 4, 4. So 4 over 24, which means that it will be 4 over 24, which is 1 over 6, right? So f of x equals 1 over 6 from 5 to 7. Now from 8 to, it looks like I either misspoke or miswrote or both down here. So from 8 to 10, something different is happening, right? And I have to figure out how to get from 8 to 3, 9 to 2, 10 to 1. All right, and when I'm looking at those numbers, I see that 8 plus 3 is 11, 9 plus 2 is 11, 10 plus 1 is 11. So these always add up to 11. So why don't I just take 11 and then subtract the s, and that'll give me the 3. 11, subtract the 9 will give me a 2. And maybe you wouldn't recognize that, and that's fine. The first two, you should be able to set up very easily. And the third one, hopefully now that you've seen it at least once where we're looking for possibly summations so that I can just subtract, then maybe you'll be able to figure out that one as well, right? It's all about seeing examples and trying new things. So here we're going to go 11 minus s over 24. And now I've got a piecewise function, all right? Now, with this, I should now be able to find some of the probabilities that it's asking me to do up here, right? It says, hence find the probabilities, Hence find the probabilities, the probability that s is greater than 2. Well, 2 would be, so this would be greater than 2. So here's 2. Everything else is greater than 2, right? So if the probability of 2 is 1 over 24, then that means if I subtract that from the total, that means everything else has to be 23. I could add them all up, but why do that? I'm lazy. So the probability that S is greater than 2 is 23 out of 24, because there's only one where it's not greater than 2. All the rest they are. All right. Probability that S is at most 6. All right. So here's my 6. So at most means that it could be anything less. Right? P could be 2, 3, 4, 5, or 6. So it's all of these down this way. Again, I'm going to try to do whatever's easiest. It looks like the easiest would be to add 7, 8, 9, 10 and subtract that from 1. You're welcome to just add those together, the 2, 3, 4, 5, 6. That's fine. But 4, 3, 2, 1 adds up to 10, which means this is going to be 14 out of 24. All right? So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 4 is 14. Okay, so that's the probability. And this is going to be really easy because I've set up the probability table. And why was the probability table easy? Well, because I could do a sample space diagram. And so you can see how a lot of these things are going to connect and link together. All right, so next is, what is the probability that S is less than or equal to 6, given that S is greater than 2? Now, here we're going to use one of our probability rules, right? Our probability laws, which is that the probability of A given B is equal to the probability of A and B, I'll make sure to get it right this time, divided by the probability of B, right? Now A is the S is less than or equal to 6, and B is the S is greater than 2. So we can go ahead and put that together. So I want on top the probability of A and B. So both of these things. So what is the probability that it's less than or equal to 6 and greater than 2? So I'm going to look at those numbers over here. So less than or equal to 6 would be this way, and greater than 2, which means I'm not going to include the 2, right? It's actually the overlap of what I did before. Right? So if you marked it properly before, which here's my yellow, right? You can see my yellow from before. That was the S is at most 6. And then you can see the green, which was the S is greater than 2. So that section of overlap right here is what I'm looking for, the intersection. So I can add those together. 2, 3, 4, 4. That would be 13. So that would be 13 over 24 divided by the probability of B. The probability of B is the second one, which is the S is greater than 2, which we found earlier was 23 over 24. And when we divide those, we can multiply by the reciprocal. So it would be 13 over 24 times the reciprocal, 24 over 23. 24s cancel out, leaving me with 13 over 23. Ta-da! There you go. That would be I. Okay, there's one last thing I'd like to look at. I actually want to go back to the first one, the first question that we did. Remember that die? I'm going to shrink this real quick and remind you of what we had there. All right, so remember this? This was the die that had 1, 1, 2 2s, and 3 3s. Okay, let's say somebody invited you to play a game. Okay, in this game, you're going to pay them $2.50. If you give them $2.50, then they will let you roll the die. And whatever number you roll, that's how much money they're going to give you. Okay? So you got a pretty good chance, 50% chance of making more money, right? You also have a pretty good chance of losing money. So what do you do? What would you do? What should you do? Okay, well, I'm going to talk about the mathematics. Of course, that decision is always up to you, but I'm going to show you the mathematics of this game. Okay, so what we're looking for is the expected value. Okay, so the expected value of a roll is actually quite simple once you've made this probability table, the probability distribution table. Because what we're going to do is kind of like a weighted average. What we're going to say is that 1 out of 6 times I'm going to get a 1. And so 1/6 of the time, my value is going to be 1. 2 out of 6 times, I'm going to get a value of 2. So that means 2 out of 6 times, I get $2. And the last one, 3 out of 6 times, I'm going to make a little bit of money. I'm going to make $3. Okay, so 3 over 6 makes $3. And what we're going to do is we're going to add these together, and this is going to give us the expected value of our random variable. All right, now we've talked about expected value before. Expected value is just the average, right? So this is on average, how much would you expect to get? Now, you can reason through this in lots and lots and lots of different ways. If you want another explanation, you can check your textbook, you can check Cognity. There's lots of different explanations for this, but really what it comes down to is when you are calculating the expected value, you take each value, multiply it by its probability, and then add those together. And that should give you the expected value. Okay, in this case, it would give us 1 over 6 plus 4 over 6, because this would be 2 over 1, so that would be 4 over 6. And then this would be 3 over 1, so that would be 9 over 6. And when we add those together, we get 9 plus 4 is 13, plus 1 is 14. 14 over 6, which if we turn that into a decimal is, well, I could do 12, so that would be 2, and 2 6 are 1/3, so 2.3 repeating. Now you'll notice that the average is less than what you paid. So we would say this is not a fair game. Okay, because a fair game is one for which you add them all together, and when you add your winnings and you add your losses, okay, whatever that may be, when you add those together, or if you consider your loss to be negative, or you can subtract them, totally up to you. Okay, but when you put your win and your loss together, you get 0. That's fair. Okay, as far as what we talked about when we talk about probability. Okay, in this situation, because you expect to get less than what you put in, this is not considered a fair game. This is one that the house, the person who's in charge of the die, they're going to make some money over time, because over time, on average, people are going to win this much money, but they're going to pay this much. So he's going to make about 17 cents every single time somebody throws the die, which doesn't mean a lot unless you have 1,000 people rolling the die, in which case he's going to make some money, right? And that's how it works. That's how probabilities work. That's how casinos work, is they always make sure that this win and loss is not 0. They always make sure that this ends up being a negative number. Like here, if I take my 2.3 and I subtract the 2.5, I get a negative number, and that's how it works. Okay, so that's it for today. I just wanted to introduce you to these concepts. No homework with this. I just wanted you to see it. Next class, hopefully we'll be able to start playing around with it and working with it a little bit. All right, that's all for today.